Good afternoon, everyone. This is Carrie Williams. I'm with TestOil, and today we have our webinar with Fred Schenkelberg. The topic is time to failure data analysis for your factory equipment. Before I turn everything over to Fred, I just have a few housekeeping things to mention. You'll notice that you are all on mute. That's because I'm recording this presentation so I can share it with you later and share it with those of you who may have to leave early or who missed it altogether. I know things come up. But if you do have questions, please go ahead and use the toolbar for the GoToMeeting under the drop-down menu for question. You can type a question in there and we'll answer it towards the end of the webinar. We will also have opportunities for you to use the chat function, which is just another drop-down menu in that same toolbar. Fred has many questions built into his presentation, and so he will be asking you to go ahead and comment so you can use that chat area to chat, and Fred and I will both monitor that. Real quick intro for Fred. He's an experienced reliability engineer. He has his own management consulting firm called FMS Reliability. I actually am pleased to have Fred here today, working with him. I've been following him for several years on LinkedIn and Twitter. I know he has a lot to say, and he's made a name for himself in this industry. He's very well known, so we're just very happy to have him. And so with that, I'm going to go ahead and turn controls over. Are you ready, Fred?
Yeah, I'm ready, if my voice holds out here.
Sounds good.
All right, well, welcome everybody, and thanks for assembling today. And if you're watching the recording, if you want to respond to any of the upcoming questions or thoughts, please let me know. I'd love to chat with you. Carrie mentioned that I'm on Twitter, and it's at FMS Reliability, and I'm also pretty active on LinkedIn, and be happy to connect with you there and start a discussion. But today, I want to talk about a phenomena I see in so many different organizations where they're, as the old saying goes, is you're data rich but information poor. And there's a couple really basic tools, real simple tools that you can use to get a better insight onto your data, or in your data, or from your data, I guess is the right word. The idea is that we collect data. We collect number of failures, we collect hours of operation, we collect, in some plants it's down to individual sensors of how often they trigger, and then what was the repair action for those. And sometimes it might be just clearing a jam, and other times you're down for a couple hours replacing a motor. A lot of that information gets collected. Now, is it serving you? Is it doing something useful for you? And so I want to talk today about one particular tool that's actually fairly intuitive, and I'm surprised it's not used more often. So let's dive into this a little bit. Get my cursor to work. So one of the reasons we want to look at our data, I'm going to back up just a little bit, is and get information of it, is that we need to make decisions. We need to look at is our maintenance program helping or hurting us? Is when we do say a preventative maintenance cycle and we change the strategy slightly, and we change the type of lubrication we're using, or we change the inspection process, or we update some tool that we're using, well, how do you know it works? Right? And is that strategy actually working or not? And so collecting data and converting that to information allows us to do that comparison, to determine if what we're doing is working, is useful or not. Another one is, well, we've got plenty of things to do, right? Even a simple factory with only a handful of assets in it will keep people busy just maintaining them and upgrading them and keeping them running. Yet, what's today's work? What's the work for next month? What's the priorities that we're going to do? Now, in more complex systems, this gets to be a very, very big project and very big product or a problem. And so having data driving your information or driving your decisions and setting your priorities can help you become way more efficient. Instead of working on what is just failed, you can get ahead of the game. I mean, many of you have heard of predictive maintenance or prognostic health management or just preventative maintenance, all of those basics. Yet you need good data and an understanding of what that data means in order to do this kind of work, to do the prioritization type things. Another one, and I mentioned it with some of these other tools, is in some cases, we're able to sense when a piece of equipment is going to fail. Now, when I first started in industry, I worked in a factory that had Warner as our maintenance chief, and he, I don't know, he must have been in his 50s or 60s, but he was this chiseled frame of a person that, and his German background, and he was very precise, and he did beautiful work in modifying and bringing in our equipment and maintaining our equipment. Yet he could walk past a piece of equipment and could hear a bearing about to fail, or a motor that doesn't sound right, or something that needed work or adjustment. He had worked in the factory for 30 plus years. He knew the sound and smells and the feel of the equipment. Now, unless you have Warner working in your factory, and even if you do, when Warner left, and if your version of him left your plant, all of that knowledge leaves. And so turning to monitoring your equipment and measuring your equipment to allow you to detect problems then takes Warner out of that equation. We still love the guy. He still did great work. And your maintenance team will get ahead of the game by being able to detect and mitigate or avoid unnecessary downtime. All of those, though, whether it's the strategy, the priorities, or forecasting problems, downtimes and avoiding it, take measurements and data. And so let's take a look at, what we can do about that. How do we get a good handle of that? Now, Carrie mentioned that I do ask lots of questions. So what kind of data do you have? What kind of repair data do you have in your factory? So give me a little bit of a clue here. Just type in the chat window if you're using a CMMS and recording jobs, or do you have good failure analysis information, or are you taking measurements of performance indicators, or just counting downtime? What are you doing? What kind of repair data do you have? And you can put that in the chat window, this little triangle to twirl that open, and feel free to chime in there. And it gives me a second to grab a sip of coffee. All right, don't be shy. You probably have some kind of repair data. Yeah, Carrie, I'm not seeing anything, and I don't get an indication if anybody's typing. So hopefully we're broadcasting. If you can hear me.
Yes, I can hear you.
All right. Well, I guess we have a shy group, and maybe I mentioned all the ones that people typically have, and so I'll drive on there. I'll be back for the chat window, so if you need some more time to find that, feel free to chime in there. Or like Carrie mentioned earlier, if you have any questions, there's a questions tab also that will help us not lose any of those questions. Get my cursor to work again. All right. So there's a couple things we do if and when you have some data. Now, I'm a reliability engineer, and I have a background in statistics. So one of the best ways to make my day, besides having a cup of coffee, is a stack of data, a set of numbers. In most systems, we track the event of a downtime and the duration of it. and it helps us to calculate uptime and the percentage of uptime that we're achieving. One of the things we also calculate is the time to failure. And so we might install an asset, or we start a run, and we set that at time 0, and then we start collecting the time hacks, the duration, the number of hours that goes until something fails. So let's take a look at some data. For those that are statistics minded, this will be a great treat. For others, it's very common that we see a quarter's worth of our data. And let's say we have 3 machines in this factory, and we pull out some information. And this is starting at time 0. And pull up my drawing tool here. Is we start at time 0, and then at 112 hours, we had a failure. And it was quickly repaired, and we moved on. And then in about 200 hours, we had another failure, and so on. So it's just a 2-column table of numbers that is just a set of numbers. Now, unless you're really, really good at interpreting a table of numbers and in sussing out what it really means, it's not terribly meaningful. Now, here's a part of this, though, is that we're going to try to compare this with the other 2 machines and make a decision of which machine do we need to do something on, which one do we need to adjust the strategy, which one should we work on, which one's our priority. So here's machine 2. Again, the first failure was at 112 hours, and we moved on from that, and we saw more failures. Now, does anybody see a difference between this one and the previous one? It may or may not be obvious. And so it's like the...
Hey, Fred.
Yeah?
It looks like people are using the question toolbar instead of the chat.
Oh, okay.
Have people communicating to there. Okay.
All right, let me take a look at it. So SAP, QMS, MPS, couple acronyms there. Component removal by, yeah, that's common. Hopefully, Lucas, you also are capturing when that occurs, how long that piece of equipment has been running, or that asset's been running. And cycle time, yeah, Dennis, all good. All right, so here's machine 2. Let me fast forward here a little bit to machine 3. It's our 3rd machine that we've been collecting data over the down events, and this is hours until the first to failure that needed a repair. Again, it started at 112 hours. That was maybe we had something unique happen then that all 3 machines went down at the same time. Yet, do they follow the same pattern after that? So let me go back to machine 1. And if you're like me, this isn't terribly fruitful analysis. I'm looking at a table of 10 numbers. Yeah, they're a little bit different, but are they really different? Which one should I work on next? Is our strategy working? Is what we're doing meaningful? And so just looking at a table of numbers is not generally all that terribly useful. So one of the things that people do is they calculate MTBF. Now, Carrie, you didn't mention that one of my websites that I started some years ago was knowmtbf.com. And it's really a site aimed at educating people about the perils of using this metric. Now, we all know that mean time between failure is a common metric for reliability related to repairable systems. And I've seen it just about in every single facility I've ever been in. And it's on data sheets, it's everywhere. It's unfortunate because it's not terribly useful. And if you want to learn a lot more about why I think it's not useful and lots of examples, go to knowmtbf.com. And so one of the most common things people do with these tables of numbers is they calculate, well, what's its MTBF? And what I think they really mean is, well, what's its reliability? How good is this equipment performing for us? But let's calculate MTBF. Now, you're going to probably sense that I contrived these sets of numbers, but I had 10 downing events, and it went over about 1,000 hours that the machine operated last quarter. Excuse me. And so our MTBF is the total operating time, which is 1,000 hours, divided by the 10 failures. And so machine 1 has 100 hours of MTBF, which in and of itself is, I don't think, all that terribly meaningful, but on average, about every 100 hours, we had a failure. And if you look at the table of numbers for machine 1, it was around 100 hours, give or take 5 or 10 hours that they had occurred. And it was almost not quite clockwork, but relatively consistent that about every 100 hours we had a failure. Now, machine 2 also had 10 failures, and it had 1,000 hours of operating time. Thus, it has a calculated 100-hour MTBF. So it doesn't really spot any difference between those two tables of numbers. And as you might imagine, the same for machine 3. Now, I contrived those numbers, so I know that they're different. And so if I stop here, if I just calculate MTBF, I would think all 3 machines are the same, and they're performing the same, and they're just fine. Yet I'll hear from the maintenance techs that machine 2 seemed to have problems at startup, and once we got it running, it was fine. So anecdotally, they're going to say, hey, we fixed a bunch of stuff up front, and now it's fine. And the other machine 3, it seems to be wearing out. I'm there more often at the end of the quarter, and there's something going on with that, and I expect to have to go there again. Now, anecdotally, we may see that in the day-to-day scheduling and the day-to-day work we're doing. Now, if it's spaced out over an entire quarter, and you have lots of other machines and equipment that you're dealing with, that gets lost in the noise. It gets very hard to detect those patterns unless it's really salient. Calculating MTBF, in this case, was pretty meaningless. It gave us the exact same number, 1,000 hours operating, 100 hour or 10 failures. And so we get the same answer. Thus, no separation, no explanation for that anecdotal evidence that we were seeing. Well, let's look at it a little bit closer. And here, and I see Dennis is on the line. I know you would know how to look at this. What do you think? Dennis, you and others, what would be your next step? How do you look at data if you're trying to detect a difference in its failure pattern? Now I've got the questions tab and the chat window open, so you can use either one. Yeah, let's say you're tasked with what's going on with these 3 pieces of equipment, and you've got a quarter's worth of failure data. And I just have shown that MTBF may not be all that useful. You know, if one machine had 9 failures instead of 10, it would show a different, better MTBF value. Yet there's still some information that's missing that we really need to know in order to pull this out. So what would you do here? How would you look at this information to help you make a decision on the strategy of your maintenance program? And these are assets. They had different kinds of failures. Let's say a labeler of some sort, say 3 different labelers on our machine and our lines, and we're evaluating what's working, what's not working. And so different kinds of failures occurred. Most of the failures were fairly quick to repair, so I'm not too worried about repair times. Yet we want to learn more about what's going on with these assets. Well, there's this tool I mentioned early on. It's called a cumulative plot. And it's a way to visualize this table of numbers. It's really all it does. It's just a plot. And it's often the first thing people do when confronted with a stack of data is let's plot it. Let's drop it in Excel and plot it in one way or another, or maybe in a number of different ways. If you have time to failure data, maybe you take those differences between failures and the duration from repair to the next failure, and you could use a histogram to see what kind of shape that has. That might be informative. Or you might do a trend plot, or you might do some other form if you have failure analysis data, maybe a Pareto of the types of failures that are occurring. To a large extent, it depends on what kind of data you have available. But here, we've pulled repair records out of the CMMS that said at 112 hours, we did a repair. At 216 hours, we did a repair. And we could dig deeper to figure out what that repair was, but let's just say, what's the pattern? What's going on there? And so a cumulative plot is, I mean, it's fairly intuitive, and it's something you should be very, very comfortable doing on a regular basis. And if you're fortunate enough, build it into your data tracking system, your jobs system, your CMMS to some extent. But basically, all we're going to do is plot the number of failures, the count of failures, the cumulative number of failures we have against time. And then depending on your asset, it may be calendar time or maybe operating time, whatever is relevant for your system. Yet, to a large extent, if you're using the system or your equipment regularly, just use calendar time. Excuse me. Let's take a look at how to build one of these things. So the basic axis is just the count of the number of repairs. Now, one of the underlying assumptions is that the repairs are affected fairly quickly compared to the total time. So if I go down on Monday morning and it's down for the entire week, and I'm looking at a time period of a month, well, that's 25% of my total time. That's pretty significant. So it should be relatively small duration of repair. So it'd be clearing a jam fairly quickly, say 5-10 minutes, up to an hour for if I'm looking at over a month. So keep it in the small single-digit percentage of downtime due to repair time in this count. Now, if you get long repairs of equipment's down for a significant amount of time, you need to keep that in mind as you're interpreting these kinds of plots. But in general, this works really well if the repairs are executed fairly quickly relative to the total runtime of your equipment. But it's just the total number of repairs. So it'd be 1, 2, 3, and so on, going up that scale as from time zero, however you define that, out to when you do the analysis, when you finish plotting it. And time, as I mentioned, is either calendar time, operating time, something to that regard. All right, so let me go to the next slide, and let's put our first data point on here. So I know it's going to be at 1. This is my first failure, and according to the data for all 3 machines, it was 112 hours. And so it's right there. Not a big deal, right? And let's go to the second point. And I don't remember from the 3 sets of data, I should have made a note. But let's say it's at 246 hours. 246, and it's my second failure point. It's that simple. And so as I get the various time hacks, I just increment up this line, right? And I get some pattern. It's the interpretation of that pattern that makes this so powerful. And we'll get into that here. So this is, from a statistician's point of view, this is a non-parametric, meaning I'm making really no assumptions. Now, I did mention that the repair times are short compared to the total time that I'm dealing with. So that's one thing to guard against. It'll add a complexity to the interpretation of these things. But just basically I'm not fitting any distribution, I'm not doing a Weibull analysis, I'm not assuming it's normally distributed, I'm not doing independent, that each failure is independent of the next one. I'm just plotting the data. And this cumulative plot allows us to take a look at the information to see if there's better questions we can ask about our system, about that piece of equipment. It also gives us some insights into the pattern of failures that are occurring. So let's take a look at some of those. So here's machine 1. And you're going to be able to detect that this is contrived data fairly quickly because it's a nice straight line. And here's 100, so it was 112 hours for that first failure, right? And so on. And if I draw a straight line through it, it's going to be pretty darn close. And so I purposely selected points that were about, give or take a little bit, 100 hours apart. And I get this nice straight line, right? I have never seen this in the wild. Real equipment doesn't behave this way. And I'll show you a couple of examples of some real equipment plots that we did, or that I did some years ago. But here I was just plotting in time and days and the cumulative number of failures, and I get a straight line. And so if I have this kind of pattern, what would you do for a strategy? If you know that at about every 100 hours, I have a failure, right? Yeah, and Dennis, good point. You could also use cycling. Just exactly right. Yeah, and here you might use a strategy that every 90 hours, I effect a repair or do an inspection. I look for, especially if it's a single thing that's failing each time, then you have a pretty dead giveaway that you've got a certain amount of time and you know you're going to have a failure. It just wears out. That component or that phenomena occurs. Or about every 100 hours, there's some glitch that occurs in the power system, or there's some phenomena that occurs, a buildup of debris, or a filter gets clogged or something like that, that forces it to fail. So it's the type of questions you can ask knowing the pattern, and that's the key thing here, right? Now, now remember that MTBF for machine 1 was 100 hours. And it's contrived that at about every 100 hours, there's a failure. And yet this machine 2, if I get it to click here for me, get my cursor back, come on. Oh, I see why. I'm still drawing, right? Machine 2, on the other hand, was also 100 hours MTBF. And for those that are very good at dealing with tables of number, notice that there were more failures in the latter half. So after 600 hours, we have the bulk of the number of failures, right? Now, what does this pattern mean? Is over time, I'm getting more failures. It's wear out. It's classic, right? Now, I don't know if it's the overall machine, sort of like my late model Oldsmobile my dad got me when I was in high school, that I think he purposely bought me this old car so I'd learn auto mechanics, learn how to be safe on the side of the road because I was there quite often. Also the expense of keeping a car running. I think he was trying to keep me poor also. But this would be very similar to the pattern that that car had in the year that I owned it. At first, it was great. I drove a couple hundred hours. I had one flat tire. Later, I replaced the muffler, the fuel pump, the water pump, fan belts. What else did it? Suspension. It just was one thing after another. And at some point, then, as you know, it's not worth driving this thing anymore. It's just failing more and more often. And we sold it. Now, if you have a piece of equipment that's showing this pattern over a 3-month period in your plant, what would you do? What would be some of the ideas or strategies that you could employ? What questions come to mind? I mean, an obvious one is, why is it showing this pattern? Why is it increasing in failures over time near the end of this thing? But also, is it the same failure, right? Is something being replaced over and over again, but it's not really fixing the problem? Or is it the machine is near the end of its life, like my old car was, and everything's getting replaced on it? Maybe it's time to take it offline and refurbish it. Yet it's a different set of questions than when they're happening, than machine one, where the failures were happening fairly consistently. All right, so hopefully you see that just a simple plot can change the type of questions that you would ask for around that equipment. And as you may already see coming, is that machine 3, in its set of data, shows a completely different pattern. And here, it's bending over, flattening out, which means that the time between failures is getting longer and longer. So here again, a simple plot. What kind of questions would come to mind here? What kind of information can you glean from this simple plot? Right? The pattern, if it's, say, a new piece of equipment, or time 0 was the start of a new run and a new setup on your line, it might suggest that you're dialing in the system. You're getting rid of the jams that are occurring, for example, or it's getting adjusted into its good operating system. Once after a couple of shifts, here it's 800 days, after a couple of years, it's broken in and it's running fairly well. But if the time scale is much shorter, it's still an infant mortality type pattern, or early life failure type pattern. So I have more failures early on, and then it breaks in, it dials in, are we ignoring failures? And, what's going on here? Is this the pattern that's consistent with the data that you have? Right? Maybe at some point somebody changed one of the main components, maybe the control board. There's an update to this thing, and the failures started to space out more. We ended up fixing a root cause, and failures started to pan out less and less frequently. Well, this is a good pattern to have, except why am I getting so many failures early on? What can I do to minimize those? How can I avoid those things? Now, the failures early in the system generally are different than the wear out failures that machine 2 is experiencing. All right, so just a simple plot allows us to take a look at 3 different patterns. And yes, these were contrived bits of data, but they give you a sense of just the simple plot can allow you to see what's going on with your machine. And it drives completely different sets of questions as to where you go do the next set of investigations. Now, depending on the number of failures and the frequency of occurring, if I was the reliability guy, I would say, let's look at machine 2 closer, because something's going on there. We're seeing more and more failures more often. We need to deal with that. Second priority would be machine 3. How can we do a setup better? How can we get it going from time 0 with fewer failures, so I can get fewer in a quarter? And same for machine 1 with that consistent pattern. Well, what's occurring about every 100 hours that's causing this failure? Now, machine 2 and 3, I wouldn't help me at all to implement an inspection every 100 hours. In this pattern in machine 3, I would miss a bunch early on, and then it would be not finding anything as machines started to work better and better. And so your strategy has to adjust to the patterns you're seeing in this system, in these 3 different systems. Great. There we go. So in real life, data is messy. And you know that, right? It's usually not 10 failures on every one of your machines over just 1 quarter, and they ran all exactly 1,000 hours. Yet the same basic patterns that you see allows you to focus in and analyze your equipment, your failure data, and your strategies in order to set priorities correctly. And that's the basis of these very, very simple plots. Now here's some data from a real system. This is run for almost a year of data. And this is the number of calls that this equipment had to go do a repair. And it had a lot of repairs in a year. But what kind of questions would you have looking at this plot? Again, it's just a time versus cumulative number of failures. And there's a couple of different patterns going on here, different things going on. Yeah, what questions would you have? What areas would you want to go focus on to see if this is working or not? Or how would you improve its performance? Yeah, now, yeah, Dennis, I'm catching up with some of the questions and stuff I'm seeing here. Yeah, mean cumulative function. Mean cumulative function is this plot, the cumulative function, and you can actually fit lines to these things. Yet what I find is that they're often pretty messy, like this one on the screen. And yeah, good. I just now realized that I hadn't been scrolling down, so I appreciate it, Dennis, all your comments. Yeah, excellent. So what kind of questions come up from this plot of data? And this is real data over about a year of collecting and looking back over a year. What kind of things jump out at you? And Dennis, I know that there's ways to do fitting a mean cumulative function to these lines and give you an idea of its curvature and slope and stuff like that. Looks like that. Let me click on the plot here. Yeah, it looks like a mix of all 3 kinds of things. Yeah, I mean, that's one way to look at it. Yeah, the plot is nice and simple, but here's one of the things I noticed. And when you start talking to the maintenance team, the nature of this machine was it's an operation. We want to keep it running. And so notice these little groupings. Let me get my pen back here. Right here, I have 4, and then 3, and then 2, and 4, another run here. These all happen within a few days of each other. Now here's another one that's more concerning. Here's 3 of them almost on, I think they were on the same day or very close to the same day within 24 hours. So what would cause that pattern for in your factory? You're running the line, the equipment's running, the priority is to keep it up, and you see these runs like this where you quickly see it, and then it seems to run pretty well for a period of time. Here, whatever they fixed really fixed it. And I actually went back and looked to see if the equipment was taken offline there or it had a major repair, and it was running. So there was some repair. Yeah, bad repair. The first one was they restarted it, and it worked. And then 2 days later, they're back there, and it's a different technician, and he looks at the equipment, and he goes, oh, well, let me try restarting it. That sometimes clears stuff, and it starts, and he checks the safety, and everything's working fine, and it goes away. He didn't really fix anything. When you go back into the records, it was basically, clean and restart. And then on this one in particular, it was removed a foreign object from one of the sensors that reduced its margin to when it would trip. And so once that was removed, the equipment ran fairly well for quite some time. And so that same phenomena explained many of these other failures. And then we got lucky that our equipment was running away from where that margin was reduced. And then it would show up again. Here again, there was this problem with this sensor, and it was adjusted. And then there were other failures that were going on here. And now we're starting to get this concave up pattern. Now, if I'm the planner or the maintenance supervisor, and I'm seeing this run 3, 4 right in a row, it's when you go out and see this machine, go check this sensor and check to see if it's not contaminated or jammed or something like that. But it's if I'm seeing this repeated pattern, there's something going on here. But I also have early on, it was overall doing this concave view, and then I got this convex one going on here. So the types of failures I get early on are probably early life failures, where here I'm seeing wear out. And so I'm looking for more details of what kinds of information am I seeing in the pattern. But the first one that jumped out to me was, well, am I really affecting repairs or looking for what's causing the downtime or causing the problem? When I see these repeated trips out to the same equipment, especially when they're accelerating like that, it's a tell in my mind that something's not really going on right. Yet it's pretty common that, the priority is, let's get our equipment up and running. And if a simple restart works, that's great. Now here's another piece of equipment in that same factory, about the same duration of time. And they have, again, it would often take them the second look before they would find something and fix it for a period of time. But here, they weren't able to follow that same pattern anymore. It's very likely that something actually is wearing out, and that it's the fixes that we've done here and here and here and other times out on this machine just are not effective anymore. So finally, the maintenance supervisor said, hey, we need to troubleshoot this thing. Let's take it offline a little bit longer and figure out what's going on. Because this kind of pattern is just spells trouble and going to cost you a lot of time and money to deal with it. But overall, the machine was running fairly well. The slope of this line was pretty flat. Except for this piece here, right? But overall, compared to the previous one, it had many fewer failures. So it was actually running fairly well compared to the other one. Let's take a look at one more. This one, I wish I had this machine and the tech for it in my plant. It's a few failures, and they're getting further and further apart. The strategy being used here is actually working. It's actually doing really well. Now, the one question we had when we first looked at this data was this machine actually running between, say, 5,000 and 6,500 hours? And it was. It actually had a couple thousand hours of actual failure-free operation, which was pretty inconsistent with what we've been seeing with the other equipment. Yeah, and you're right, Dennis. It's part of asking these questions then drove us back into the maintenance logs. What was repaired, what was replaced, what was cleaned, what was done to keep it up, what we're seeing in the preventative maintenance cycles. Now, this data, this actual data, was just corrective maintenance. And the logs by some technicians were really, really good and fairly informative. And others, it was pretty sparse what was recorded. But as we sat down and talked to the various technicians and showed them this data and started asking these questions, we would get anecdotal evidence. And then some things going, you know, I don't remember, I should have written it down. Well, yes, that would be helpful. The other part of this was that as we started looking through the data sets, get back to my, right, and you just see the differences and patterns here, is this equipment with all of its failures was also about 15 years older than our other equipment. And this one, with far and few between failures, was relatively new. Same basic maintenance strategy, yet when we started looking at the cost of failures, the cost of the downtime we were seeing on this one, became obvious that we really did need to replace this one or do a total overhaul on it to get it back up to speed. But having this data made a tremendous impact on the operations manager to say, oh, this is obvious, I need to fix this. This is really costing us money. And here's the evidence, here's the data that shows those differences and patterns. So this is just 3 machines set side by side. You could plot them all in the same plot and show it that way. We did things like that also. Yeah, and Todd, this is our first look at the data. So I was brought into this organization to take a look at their field data. And this is looking back and seeing what we could get. But your point of being reactionary is very good. And I agree with you that when you're looking back on your data set or looking at what happened last week, you remain in, these are all corrective actions and called out to you. Yet, here's one of the things that we noticed is that when we saw this pattern, these 2s and sometimes 3 repairs fairly one right after another, is the previous policy in this past year was pretty consistent across all 3 of these machines that I showed you so far, is get it running, do a restart. Unless there's something obvious, just do a restart, check it out, see if it shows the problem again, and then effect a repair. But we saw this repeated call out to this equipment so many times that we changed the policy that on the first time, take 10 minutes and do a bit more troubleshooting. Here's the short list of things that in these machines are the problematic ones that on our second and third call, we would find. So let's change the policy so that on the first call, you go fix it. There's something wrong here. And a restart and standing there and watching it for half an hour while it operates isn't quite long enough for that failure to show itself again. But if you spend a bit more time and clean some sensors and check some alignments and the short list of things that we really need to do, it becomes a mini preventative maintenance action, yet it stopped that second call out in a couple of days. And so it's taking the same set of patterns and looking for ways that we can get ahead of it. Is our current strategy working or not? And the long story in this is that by changing that strategy, spending a few more minutes on the first failure, yes, we found things that we just couldn't figure out what caused the problem, and sometimes we get called out again, sometimes we didn't. But we reduced the number of short recalls, basically going back out to that equipment within a few days by 70%. And so we knocked out a significant number of corrective repairs just by doing a little bit of due diligence. And it was a compromise. We wanted a half hour of troubleshooting and preventative maintenance, and we got 10 minutes, so we took it. And it was enough to make a huge difference in the way this particular set of equipment operated and its maintenance worked. Oh, one more piece of equipment. This was one of my favorites. It was getting old. The technician on it really didn't like this equipment. I think he had a personal problem with it. Yeah, and we saw these. It was almost every shift this tech was on it, this equipment failed, and he would go out and he would just restart it. And so we ended up with these long runs of repeat calls. That one, not so much, but this one. And then finally, the maintenance supervisor would send somebody else out there, having known that this equipment has failed like every day, every shift, it's just going down. We need to fix this thing. They'd send another team out there, spend a little bit more time on it, and they get some more time on it. Yet there was still this overall pattern of lots of failures. And so it was time to do a more of an overhaul on this one, much like that first machine I showed you that had lots of problems. And so, but the basic strategy of dealing with these kinds of runs, and once we saw two of them, we knew that we failed on the first call out. So the maintenance techs and the operations manager agreed to spend more time on the first one. And so unfortunately, I don't have the data from the second year to share with you, but take away about 30–40% of the failures, and especially these patterns that occurred like this. They almost completely eliminated those. Now that's unique to that particular set of equipment and situation. I'm sure in your factory, you'll see different patterns. But the idea is that those patterns allow you to start asking better questions. You know, I don't know if it was lazy tech, Dennis. I think that it was, I restarted, I stand there and I watch it for half an hour, and I could be working on preventative maintenance on other equipment. I could be doing something else. The failure doesn't repeat itself quick enough. And just that policy of restart it was the culture, was just clear the errors unless there's something obvious, clear the errors, run it, is it safe, turn it back on, put it back in production. And so that was the policy. That was the procedure that was laid out for the techs to follow. Now the better techs, they got tired of going out and seeing, looking at the same equipment. So despite the policy, they would check a few things and try to fix things. So we saw differences between techs, which gave us the clue of let's change the policy. I don't think it was the tech's problem or fault. I think it was the policy's fault and the procedure that they were instructed to follow. And so we changed the policy and rewarded finding and fixing the problem the first time. And so the basic idea is all I had in this data, and we pulled it from CMMS data where they just log the repairs, the calls for a tech to come see this equipment. We converted it to time to failure data, or time, just when did the failure occur relative to some time zero or start of the year in this particular case with real data, and just counted failures. The patterns were striking between different types of models of equipment, between different technicians, between different locations and different use patterns that the equipment had. It helped us to tell a story about our maintenance program and inform us of what we could do to improve the strategy to deal with this equipment. It certainly helped us focus on priorities. The equipment that was causing the bulk of our problem really did need some serious work and retirement in some cases and bringing in new equipment. But now we had the data to show the impact of this equipment just falling apart or wearing out. We also saw the direct impact of a slight change to our strategy. Instead of restart and check it, it was check it, then restart. Clear up a few things, clean a few things, adjust the alignment, especially was a couple of the areas on this equipment was an alignment issue that wouldn't cause it to fail all the time, but would cause it to fail frequently if it wasn't kept in tolerances. And so a quick hour check, you wouldn't necessarily find it. Whereas checking the alignment you wouldn't have to come back to this equipment for a couple of weeks. And so it made a huge difference in our particular case. Now you can also, and Dennis, you've mentioned it a few times here in the questions tab, is there this mean cumulative function and the ability to look at recurrent data, you can fit lines to these things and fit patterns, and you can put, especially if you have the same kind of equipment, and you can get a fleet type pattern going on and do more sophisticated things. But even just the simple plots on different pieces of paper just helped us make tremendous strides in interpreting the data that we already had available. Now, that's the first step. Start gathering the information and take a look at it. And then it's move forward to what can you do to make improvements in your factory, and using this data as a guide or a clue as to where to make the improvements. And so, find my cursor again. There we go. So I think that's all I've got right now. I appreciate, Dennis, all your support, and a handful of others I saw chiming in on the questions tab. Yeah, simple comparisons, good maintenance practices. Yeah, you got to get ahead. You got to get onto the condition-based monitoring. You know, part of what we saw, Todd, was that as we learned these patterns, is the condition-based monitoring wasn't used at all in this plant. It was basically fix on failure for about everything. But for some of the types of patterns we saw that were clear wear out patterns, some of those older pieces of equipment, we started looking at, it was more not just alignment, but the motors and the vibration we were getting was knocking the alignment out more often. But it took us a little while to figure that out. And so we started looking closer at our motors and motor alignment, and also replacing a number of bearings, which takes longer. We had to plan for that and do it offline. Yet it allowed us to start realizing that monitoring the amount of vibration over time gave us a pretty good indicator when we needed to do more major repairs. So some of that condition-based monitoring, we built a case for to bring it into the plant to actually start doing it. But prior to that, it wasn't even a consideration. Yeah. And so I've got a couple of links on the screen here. One of them is podcasts. If you like listening to podcasts, if you're in a commute or if you got a time when you can listen to a show, there's a reliability.fm is a podcast network, and there's, I think, 5 shows on it right now. We're working on bringing in another one that's a bit more on the design side of product development, more of a Six Sigma, a Lean Six Sigma, that type of topics. But there's James Kovacevic does Rooted in Reliability, which is an excellent show on maintenance engineering, maintenance reliability type topics. And speaking of reliability, touches on the topic every now and then. There's a bunch of other procedures and recorded shows and webinars. AscendoReliability.com is a project of mine, along with about 15, 20 other people in the industries, that is looking at developing a hub for professional development. And there's free courses, or there's free webinars, podcasts, articles. There's about 6 to 10 articles per week from a variety of authors. And then there's a handful of courses and in books and references and stuff like that. The site's free to visit and to become a member of and get access to more information, more content. There's a couple of free ebooks on maintenance practices underneath resources or under ebooks. And it's non-denominational. It's really looking at all the different industries that are doing stuff. So things like the Test Oil webinar series will advertise that and list those that when they have, like this one, have something to do with reliability engineering. We're happy to share those so you can find it. So let me check the questions tab. Carrie, I think that's all I've got. I think we're also coming up close to the end of the timeline. Let me see what other
you really
questions
did
are.
stop with all the questions, because I don't have any to ask you at the end here, which is what we typically do, since you answered them really nicely throughout the presentation. So I think we're going to go ahead and close it out. We've reached our hour, which is the maximum we like to do for these webinars. And Fred, thank you so much. I really enjoyed your interactive webinar. Not many people use the screen and write on it and ask questions and get people to comment so much. So it was really an interesting webinar to see all of that interaction with all of our guests. And thank you all for attending. And I'll send out the recording a little bit later today. I'll also include a PDF of all the slides from Fred. And if you have any questions, I'll include his email and contact information so you can get directly to him for some follow-up questions if you have them.
Yeah, thanks, Carrie. Appreciate it.
All right. Well, y'all have a great day. Thanks, everyone. Bye-bye.